In this screencast, we're going to look at a reaction taking place in a steady state CSTR, but we're going to have multiple solutions to the mass and energy balances. This is CSTR with heat exchange, so we're given various properties and flow rates. Note that in addition to two reactants A and B, we also have an inert, methanol, that we need to take into account. The reaction is first order in A and zero order in B, and we're given a rate constant, an activation energy, and a heat reaction. And so you should look at all this information about what's known about, in this case, the heat transfer coefficient times the area for heat transfer is given, and the heat transfer temperature, which we're going to assume constant as a reasonable first approximation. So the question is, what are these steady state operating conditions? What we'll calculate is the temperature and the conversion that are the multiple solutions to this particular CSTR. Now, the first thing we want to do is make a drawing that represents the process to make sure we have all the information and list the important parameters that we're going to use. So I've drawn a diagram to represent the process, listed the feed conditions, the unknowns, namely the temperature and the conversion leaving the reactor. I should also indicate the volume of the reactor, remember it's a steady state, and then I've listed the various parameters that we're going to use in the solution. So now the first thing I want to do is write down a mole balance. Because my approach to solve this when I know I have multiple solutions is to write down the mole balance and the energy balance and plot the conversion versus temperature that I obtained from each of those equations. The intersections are the steady state solutions, and that's an easy way then to get the solution using something like Excel to make the plot. So first let me look at the mole balance, and I'll do the balance on A, the reactant, steady state, no accumulation. A flows in, A leaving is what we don't know. Then we have a rate reaction per volume times the volume. So we can write this, since we want to be able to calculate the conversion function of essentially temperature. FA0, that's a constant. I'm going to write this as the volumetric flow rate times the concentration. Since this is a liquid phase, the volumetric flow rate is going to stay constant at 25 cubic meters per hour. And then the rate of reaction, since it's first order, minus sign, reactant, K concentration times volume. Now I've written it this way, so now I can solve for the concentration of A. So let me just rearrange and solve for the concentration of A. So I solve for concentration of A in terms of K, flow rate in, the volume reactor, volumetric flow rate. Notice that the concentration leaving is the same as the concentration reactor, well-stirred CSTR. Now I want to calculate conversion. That turns out to be an easy parameter plot as a function of temperature to solve this. So first I'm going to calculate the flow rate. So the flow rate of A leaving is going to be the volumetric flow rate times the concentration of A. Substituting in here, FA0 over the volumetric flow rate K times volume. And then I can rearrange this. So I've written the flow rate leaving reactor in terms of the entrance flow rate, the rate constant, and now the space-time, the volume of the reactor divided by the volumetric flow rate. Now I can then calculate the conversion, inlet flow rate of A, exit flow rate of A over the inlet flow rate of A. And if I substitute this into the equation, end up for expression for X when I do the algebra, and tau, my space-time, is 20 meters cubed over 25 cubic meters per hour. So tau is 0.8 hours. And the rate constant times tau, I'll calculate that. So I have a value of K times tau, which is dimensionless. We're going to substitute this into this expression. I can make a plot of the conversion versus temperature, because temperature is the only variable now in K times tau, and I can plot that as 1/2 of the plots that I need to determine the solution. So now I need to solve the energy balance. So I'm going to write the steady state energy balance. Steady state, so there's no accumulation term. There's a term due to the fact we're flowing A, B, and M into reactors. So flow rate of A, the heat capacity of A, and then likewise for B, and then likewise for the inert M, heat capacity of M. So we could look at this term as energy would take the heat up. If the reactor temperature is higher than the feed temperature, it requires some energy to heat up the feed. And then we have the heat reaction times the rate of reaction times volume of the reactor. And then we have a heat transfer term, coolant temperature minus the reactor temperature. So I'm going to try and simplify this and make the terms a little easier. FA0, FB0, FM0 are equal, so we can write them all as FA0, and then times alpha, where alpha is just the sum of these three heat capacities. R sub A times V is FA minus FA0. R sub A times V is a negative number because R sub A is minus KCA, and so FA minus FA0 is negative, and that's, if we plug in the mass balance, that's the equality we could get. Now I'm going to divide this by FA0 and simplify. Now I'm going to do a few things. I'm going to calculate the value of alpha. I'm going to calculate the value of UA over FA0. Also, notice that this term here is minus the conversion. And so I'm going to calculate these values and then substitute in. So I'm going to substitute alpha and then this ratio and x into the equation, and then I'll rearrange it. Made the substitution, check the units, our joules per mole for each of the terms we're adding together. Now let's just simplify this equation. And so now I have an equation for x in terms of T for an energy balance. I also have x in terms of temperature from the mole balance. And what I'm going to do is just plot those with Excel, and then I'll show you the plot that I get. So I plotted conversion versus temperature of XL. This is the energy balance, straight line. This is the mole balance. These are the steady state solutions. This is an unstable one, but for now we're just interested in, you can read off the graph at these three temperatures. Here are the corresponding conversions. This is the objective of the problem to determine what the steady state solutions to the mass and energy balances are.